Today, we are tackling one of the most mind-bending experiments in all of physics, one that seems to poke a hole in our basic understanding of time and reality itself.
So let's just jump right in with the big one, the central question. Can a choice you make right now, in the present, somehow reach back and change something that has already happened? I know, it sounds like something straight out of science fiction, but a very real experiment seems to flirt with this very idea.
But before we can even touch the quantum eraser, we gotta rewind. We have to start with the granddaddy of all quantum mysteries, the one that's been baffling scientists for 100 years, the double-slit experiment.
All right, so here's where things get, well, really weird. You see, down at the quantum level, tiny things like photons, particles of light, don't play by our rules. They can act like a solid little object, like a tiny baseball, but they can also act like a spread-out wave, like ripples in water. It's called wave-particle duality, and you have to get your head around this because it's the key to everything else.
This is where the mystery really kicks in. If we shoot photons at a barrier with two slits in it, and we set up a detector to watch which slit each photon goes through, they behave perfectly normally. They act like little baseballs and land in two clumps on the screen behind the slits. Simple. But, and this is the part that blows everyone's mind, if we turn off the detector, if we don't watch, they stop acting like particles and start acting like waves. They produce this beautiful interference pattern of many stripes, which could only happen if each photon somehow went through both slits at the same time. The very act of looking at it changes what happens.
All right, so physicists see this and they think, okay, observation seems to be the secret sauce here. So they got really clever, they cooked up this brilliant, totally weird question. And that leads us to the delayed choice twist. The idea came from the legendary physicist John Wheeler, and it was as simple as it was profound. He asked, what if we measure which path a photon took, but then after the photon has already landed on the screen, what if we could somehow delete that measurement, just wipe the information clean? Could we bring that wave pattern back from the dead?
And get this wasn't just some late-night philosophy session. Wheeler dreamed this up back in 1978 as a thought experiment. But then, in 1999, a team of scientists actually built the thing. They took this wild what-if idea and turned it into a real working experiment in a lab.
So you're probably asking, how on earth did they pull that off? Well, the secret ingredient is maybe the most famous and spookiest part of quantum mechanics, entanglement. Let's follow the photons.
Okay, quick crash course on entanglement because it's super important. Imagine you have two particles that are fundamentally linked, like a cosmic duo. If you measure something about one of them, you instantly know the same thing about its partner, even if that partner is on the other side of the galaxy. It's this weird, spooky connection that makes the whole experiment possible.
All right, here's the setup, step by step. First, a laser zaps a special crystal, and poof, you get a pair of entangled photons. We'll call one the signal photon and the other the idler photon. The signal photon has a really short trip. It goes through the double slits and hits the detector screen. Bam, done. But its twin, the idler, takes the scenic route. It travels to a whole different set of detectors and mirrors. And this is the clever part. That second setup can be configured to either tell us which slit its partner went through, or it can be set up to completely erase that information.
And look, this isn't smoke and mirrors. This is some seriously high-tech engineering. We're talking lasers, special crystals, super-fast detectors. The whole point of all this gear is to do one thing perfectly, to match up the arrival of each signal photon on the screen with the information we get from its idler twin just a few nanoseconds later.
Okay, now for the payoff, the results. Remember, the signal photon hits that first screen before its twin even gets to the part of the maze where we decide to get the path information or erase it. So its fate should already be sealed, right? Its behavior should be locked in.
But when you first look at the main screen where all the signal photons have landed, it's a mess. A total mess. It just looks like a random cloud of dots. No two clumps, no interference stripes, nothing. You'd think the whole experiment was a bust. But hold on, this is where the absolute genius of this thing kicks in. The secret isn't that we're changing the past, not at all. The secret is in how we sort the data we have right now. The magic is buried in that random-looking mess, just waiting to be uncovered. So here's what the scientists did. They started sorting. They took all those random dots on the main screen and split them into different piles based on what happened to their idler twins. First, they looked only at the signal photons whose twins gave away the path information. And bam! When you look at just that subgroup, you see two distinct clumps, a perfect particle pattern, no interference. And then they looked at the other pile,
The photons whose twin partners had their path information totally erased, and when they isolated those dots from the exact same dataset, it was like magic. Pulled right out of that random noise, there it was, a beautiful, clear interference pattern, a wave pattern. Both realities were there the whole time, mixed together, just waiting for us to sort the data and reveal them.
Okay, deep breath. So what is actually going on here? Did our choice to erase information in the present really reach back through time and change how the photon behaved in the past? Well, I'm sorry to burst the sci-fi bubble, but no, that's not really what's happening.
This is the big misunderstanding. People hear about this and jump to retrocausality, the idea that the future affects the past. But what's really happening is about correlation, not causation. We aren't changing what happened, we're just using information we get later to sort the results into different buckets. The patterns only emerge after the fact, when we combine all our data. No information is actually being sent back in time.
But the real takeaway here is still absolutely mind-bending. What this shows is that at the quantum level, physical reality and information are inseparable. If the information about which path the photon took exists anywhere in the universe, even if no one ever looks at it, then boom, it acts like a particle. The wave pattern is gone. To get that pattern back, the information can't just be ignored, it has to be fundamentally and completely erased. And this isn't just some weird puzzle for physicists. This profound link between information and reality is a cornerstone of real-world cutting-edge technology. We're talking about things like quantum cryptography, creating unhackable codes, and the very foundations of quantum computing. Which leaves us with one last big question to chew on. This experiment proves that there are hidden patterns in reality, patterns that we can only see when we know exactly how to look. It suggests that reality isn't just a fixed, solid thing. It's conditional on what is knowable. So if our reality depends so deeply on the information that's available, what else are we not seeing? What other patterns are out there, hiding in plain sight, just waiting for us to ask the right questions?